All right, okay, so just a reminder of what we were doing this morning. We were looking at Taylor series, okay? Now, I realised we went through it in a slightly rushed way, so I just want to reiterate what we did this morning to make sure it makes sense, okay? So, Taylor series is all about taking a function which doesn't particularly look very nice, okay? Something like cosine of x. The reason why I say it's not a nice function is because it's not a polynomial function. It's not something that looks like this, okay? And you remember using a polynomial function is a much nicer function to use because it's easier to extract the roots. It's also easier to differentiate. You know, it's much, much nicer to use, okay? So the whole idea is, well, can I take something like this? Can I take cos x and can I approximate it using a polynomial? And the answer is yes, okay? The way which I do it is by considering the derivatives. Now, I just want to be clear about what these derivatives, like what they correspond to on the graph, okay? So the first thing I need to think is, right, I need to make sure that at this point here, at x equals 0, so this is the point which I am approximating my function around, okay? At x equals 0, the actual value of the function itself, so like the point, has to be the same, for my polynomial, has to be the same as my actual function, okay? So the value of my function at the point x equals 0 has to be the same as the polynomial which I'm approximating, okay? And I can get that really easily by using this constant here, okay? So C0 is basically the value of the function at that particular point, okay? So I just simply put x equals 0 into my function, okay? And that's my point. And I'm like, come on, I'm approximating this. I need to do better. So why not consider a straight line, namely the tangent line? That's a better approximation than just a single point. Are you happy with that? Okay. So the tangent line, or the gradient of the tangent line, will be given by the first derivative. So I'm basically saying, if I differentiate this function once, ignore all of those terms, if I differentiate this function once, I'll just be left with C1, because you're happy C0 is just a constant. If you differentiate it, it just drops out. So basically, if I differentiate the function once, it will just be given as C1, okay? And I'm basically saying that that constant should be the same as the first derivative of my function, and then I plug x equals 0 in. And that will give me the value of my tangent line. So what I'm literally saying here is that the first derivative should be the same as the first derivative of my function at that point. Does that make sense? Okay, so that's what I've drawn in blue, my tangent line. Then I go, come on, I can do even better than that. I can consider 3 terms of my polynomial. Okay, so my third term will be my quadratic term, or my x squared term. So if I differentiate it twice, these first 2 terms just drop out. Okay, they just drop to 0. And I'll just be left with not quite C2, because if you think about it, if I differentiate this first 3 terms, if I differentiate it 3 times, okay, so f of x is C0 plus C1 times x plus C2 times x squared. If I differentiate it 3 times, well, the first derivative is going to just be C1x plus 2C2x, almost. Yeah, C1 plus 2C2x, okay? But then if I differentiate it again, then I get 2 times 1 times C2, okay? Because I've differentiated it twice. You just think that's a power there. That power climbs down, so it becomes 2 times 1 times C2, and the x just goes to x to the power 0, okay? So therefore, it's equal to 2 times 1 times C2, that's my second derivative. That should be the same as the second derivative as my actual function, and then I stick x equals 0 in. So it should be the same as negative cos of 0, because I'm approximating it around 0, okay? And then I can keep going. I can say, what about the third derivative? That's going to be an even better approximation of my function. And again, I can think about it. So this term, and this term will drop out now. And this term, well, if I differentiate 3 times, first derivative is going to become 3 times C3x squared. Second derivative is going to become 3 times 2 times C3 times x. The third derivative will become 3 times 2 times 1 times C3. Okay? Hence I get that. And that should be the same as the third derivative of my function when I stick 0 in. Okay? If I want it to be any good approximation. So what hopefully you're seeing here is with every iteration of my Taylor series, in other words, as I can consider more and more terms in my Taylor series, what I'm doing is I'm considering a wider interval for which my actual function is being approximated. So for example, for this first approximation, so just the equal to the value, I'm just considering a point. Not a great approximation, but not a bad one, okay? For a better approximation, I can consider more terms, so consider the first derivative. That's just going to be a straight line. So I'm basically saying, imagine that this function is just a straight line, okay? And then if I want a better approximation, I can consider my second derivative. Well, that's now going to be a quadratic. Well, a quadratic is going to be a wider interval than just a straight line. Are you happy? Yeah? So if you imagine that this is actually my curve, if I zoom in on this particular point here, okay, I start off with something that looks like this. So this is my actual function around the point x equals 0. Okay, so that's my point x equals 0. So I've literally just zoomed in on this point down here. Does that make sense? Okay. So for my first one, it's just simply a point. I'm just approximating it as a point there. Fine. Okay. For my second term, I'm now approximating it as a straight line. Now, are you happy that that's a wider interval for which this actual curve matches with my approximation? Yeah, because it's no longer just a point, it's now kind of a little bit outside the point as well, like just a tiny little bit. Then if I consider my second derivative, well, now I'm approximating this as a quadratic. So, okay, so I get something that looks like this. Well, now my interval of kind of where my function best matches up is sort of, say, from there to there. Does that make sense? So I've gone from pretty much just a single point, and then for my blue one, I've gone from there to there, and then for my actual quadratic, I've kind of gone from there to there. Now if I consider my cubic, I get something that looks like this, okay? So now my approximation for where my function matches is from, I don't know, so there to there. So can you see that with each iteration, each term that I'm considering in my function, I'm considering a wider interval where my approximation matches my actual function, okay? Now clearly this is a series, it's an infinite series, because I put these 3 dots there. So if I carried on going forever and ever and ever, eventually, theoretically, I should have a function which matches this, not just around some interval, but around the entire function, okay? Now, of course, it's impractical to do this for an infinite number of iterations, but I think, because we're only looking for an approximation at a particular point, 3, 4, 5, maybe even 6 terms would be a good approximation around that particular point. But obviously, if you wanted it to be even more accurate, then you would consider more terms in your Taylor series. Is that okay? Okay?